everybody. Today we came very, very close to having a physics first. I was looking at the clock and it was 4:15, 4:20, 4:25, and nobody was here. And I thought, what if nobody comes? And I had completely resigned myself to talking like a crazy person in front of a projector with nobody here and hoping the custodial staff doesn't walk in. But if they did, I mean, that's fine. They already know that I'm a strange human being. But then, minutes before we got started, Mr. James came running in to my rescue. So now I'm giving this to an audience of one, at least in person. I don't know how many virtually. Let's go. Um, so the test is going to consist of 15 multiple choice questions, 2 points each, one lab based question, that's worth 10 points, 5 free response questions, those are 10 points each, and you'll have a full 90 minutes to do it. Typically, it does not take 90 minutes for people to finish the test. Some people it does. That's exactly how I was. I was always just hanging on to it until the last minute. Um, but you've got that whole time, so make sure you bring something else to work on just in case you finish early, so you're not just sitting there bored out of your mind while everyone else is being super quiet and taking a test. Um, you are allowed to bring one sheet of paper front and back. And you can write anything you want on this piece of paper. So I would include all the equations that you need, because I'm not going to give you equations on the test. I'd include all the variables, what they mean. Maybe do some example problems just so you've got that squared away there. And some of the most important concepts. Um, Make sure you got those down pat as well. You are going to need to bring a calculator, and I've got 92 students, but I do not have 92 calculators. Well, I guess I got 24 in a class, but I don't have 24 calculators either. So make sure you bring one, and if you don't, just let me know ahead of time, and I'll have a calculator set aside with a little sticky note with your name on it. All that kind of good stuff. I know a lot of people in class like to use their cell phones as calculators, and that's great, but that's unfortunately not going to fly on a test because your cell phone can do other things that probably shouldn't be available for you while you're on a test. James is disappointed. All right, some resources that you have to look at. On modules 1 and 2, I still haven't taken any of those lessons down. In fact, if you go back and look at lesson 1, lesson 2 all over again, odds are they're going to make a little more sense now that you've had a bit of practice in class with them versus when you were first reading them and being introduced to the topic before anyone else is there. We have a second. Claire is here. Hey, I'm so excited. We just doubled our audience. You do have a textbook. I put that in Canvas right on the physics homepage. There's a link to it. If you click that link, you'll automatically start downloading that PDF. Um, so take a look at that. That's going to cover chapters 1, 2, and 3 in that textbook. If you want to just see how someone else words some of these same kind of concepts. I also mentioned this in class, but I've posted last year's test 1 along with all of its solutions right there on Canvas under the module Test Solutions and Review. Not only that, you can go back and look at the quizzes, either that you've taken or haven't taken. All the solutions should now be available. So if you want to run through some practice problems, mainly concept-based, that's a good place to do that. You can always go back to old WebAssign problems as well. If you click the past link up on WebAssign, it'll take you straight to all our past assignments, so you can always view those too. Let's get going with the stuff you need to know. 1. Metric prefixes. You absolutely need to know all of these metric prefixes that I've listed here. The larger than base units in maroon, and the less than base units in a friendly cyan right there. So make sure you know at least these. There are plenty more, but these are the ones that you're going to need to know in physics class. By the end of the year, you really should have these committed to memory, and just be able to bounce between one or the other really quickly. If it helps, this is the metric staircase here. You can start with your base unit, and the number of steps one way or the other tells you how many places you need to move the decimal point and in which direction. So if I'm traveling from, let's say I've got centimeters and I need to know how many kilometers that is for whatever reason, I can find that simply by moving my decimal place 1, 2, 3, 4, 5 places to the left, and that's it. So if the metric staircase helps you, then keep the metric staircase. If it doesn't, then forget the metric staircase. One correction that I have for this little image that I found: meters are base unit, liters are a base unit, grams are not. The kilogram is the base unit of mass. Um, that's the one slightly different, weird one. I'm going to give people here just a second because they're both writing furiously, so I'm going to sit back. And what's that? Oh, a dead pen. Yes, I have pens. Where did they all go? Is a pencil okay for today? Awesome. Thanks. Cool. All right, forward. Unit conversions. Not only do you need to know what the base units are, you gotta be able to convert them from one to another with ease and delight. First and foremost, you're going to want to look at your current numerator and denominator, if there is a denominator. Ask yourself, what units do you currently have, and make sure you list it in fraction form. So for example, if I have a velocity of 3 miles per hour and I want to convert that to meters per second, then I'm going to write that as 3 and the fraction miles per hour, with miles clearly on the numerator and hours clearly on the denominator. A lot of units don't have denominators, and if that's the case, like 3 miles, and I want to know how many kilometers that is, then I can just write it as 3 miles over 1 with nothing in the denominator but a number 1, just to help with that. Afterward, you're going to have to look at the final numerator and denominator of the units you need. So I start with miles per hour. I need meters per second. And then you'll set up your conversion factors to cancel the units you don't want and to introduce your final units. So if I have my 3 miles divided by hours and I'm trying to get to meters per second, I'll get rid of the miles. Since they're already on the numerator, I'll put them on the denominator. That'll cause them to cancel with each other. And I'll replace that with a meter. I'll get rid of the hours by putting it on the numerator, so it'll cancel with the existing hours on the denominator, and put seconds down in its place in the denominator. And after all is said and done, I'm left with just meters in the numerator, just seconds in the denominator. So once you get these conversion factors set, you'll solve for a new number, and it'll be in units of meters per second. And joy will abound throughout the land. We did a lot of practice with this early on, so look at some of our earlier stuff if you need a little bit of unit conversion practice. Just a quick reminder: when you're adding or subtracting, you can only use identical units. This goes back to the raccoons breaking into my basement and me feeding them cupcakes. I can't add a raccoon and a cupcake together, but I can add raccoons and raccoons together, or cupcakes and cupcakes together. And the unit remains unchanged. So 2 raccoons plus 3 raccoons equals 5 raccoons. Done. With multiplying and dividing, you can do that with any unit. Anything can be multiplied by anything, anything can be divided by anything, but the units have to carry through basically as variables. If I've got some some value of distance and some value of time, and I divide them, 8 meters divided by 4 seconds, then that means my units also get divided the same way. I end up with meters in the numerator, seconds in the denominator. You just treat them like variables like that, and you're golden. By keeping track of these units, you can tell whether or not you make a mistake before you actually make it, in case you're trying to add something with units that are not alike. Then you know you've done something wrong already. Go back and fix it. That'll save you a little bit of time, or a few points on it, just in case. So a lot of times I recommend doing the problem once with numbers and once with units, and seeing how that all shakes out. Then got to significant figures, everyone's favorite topic in every science class. Um, so a couple of things. First, how to tell whether a number is significant or not. Any digit that is 1 through 9, automatically significant. That part's easy. Always count those. If you've got zeros on the left of a decimal point, they follow slightly different rules than zeros on the right of a decimal point. On the left, I said decimal point? Decimal point? It's been a long day, y'all. Thanks. Thank you, James. I can always rely on you for moral support. Okay. On the left of a decimal point, they are significant between any other sig figs. If it's after the final known sig fig and before the decimal, then it's ambiguous, and I'm honestly not going to ask you a question about how many sig figs are in the number 480, because it could be 2 or it could be 3. What I will ask is how many significant figures are in 4 squared, because now, oh, by the way, anytime you're in scientific notation, the times 10 to the power plays no role in the number of sig figs. That helps at all. You'll just look at the leading number to tell how many sig figs are involved with it. So I've got 4 that's significant, I've got 8 that's significant, and 0, let's see. Any final zeros that are on the right of a decimal point are significant. Well, that's what this one is. Nice. It's also going to be significant between any other significant figures, such as these 2 zeros, because they're between a 2 and a 3. What will be insignificant will be any leading zeros, so 0.0000002. That has 1 sig fig, and that's it. I could continue to add zeros after the 2, and that would add more sig figs to this number, but that's that. Now, once again, just because something is not considered a significant figure does not mean it's unimportant at all. Because if you take away all of these zeros, that changes the value a heck of a lot. But what it does mean is that when you calculate your final answer, it tells you how to round your final answer. That's all that significant figures are really good for. So let's talk about how to do that. When you're adding and subtracting, you'll look at your arguments beforehand, and by arguments I just mean values, incoming values, and you'll look at decimal places, not sig figs, and round your answer to the least number of decimal places. So I want to make that super clear here. Whoops. So adding and subtracting, you don't care about sig figs, just raw number of decimal places is all you're really looking at. Sig figs matter in multiplication and division. And that's about it. Typically, if you're doing a multi-step problem, I'm going to recommend holding on to all, that full value with a ridiculous number of decimal points. If you make intermediate calculations along the way, just round your final answer at the very, very end. Because if you round ahead of time, then any calculations you do from there on out will be slightly incorrect based on how you round it. So just be careful about that. Yeah, and that's about it. So multiplication and division, it's all about the sig figs, the least amount of sig figs. Adding and subtracting, it's all about the least number of decimal places. Cool. Question, yeah. Mhm. Right. Oh, gotcha. Okay. So the question is, if you had an incoming number of 2.3 and you were adding something to it and you ended up at, did you say at 2.4? Oh, something past that decimal point. So 2.4. All right. So let's say 2.3 plus 0.123. Technically, that would come to 4.423. But because the least number of decimal points is one decimal point, you would end up rounding that to just 4.4, which is weird. Huh? Oh, shoot, that's two. Oh, I'm so tired. Wow. Fun fact, folks, 2 plus 0 is not 4. 2 plus 0 is 2. Oh man, I'm teaching you all college level physics, and I don't know how to do 2.3 plus 0.123. Yeah, okay, sounds good. Oh man. Then we started talking about vectors, and we did a lot of vector math. Vector is anything that has magnitude and direction. So mass, for example, is not a vector because I don't have 70 whatever kilograms up, down, left, right, um, or anything like that. I just have 70 some kilograms. That's it. But velocity is a vector because I can be traveling at 5 meters per second north, or I can be traveling at 5 meters per second south, and what results from that is way different, even though my speed is the same. Um, so it has to have magnitude and direction. Usually, you indicate the angle above the x-axis, and if you throw a negative in front of a vector, all that means is that you're flipping its direction. So when we're problem solving with vectors, a lot of times I tell you to indicate which direction is positive and which direction is negative. So if I've got a vector with a y component of -2, I know that means it's a downward component of 2. Or vice versa. You are welcome to say down is positive, and any math you do will come out just fine as long as you keep track of what you're doing there. Mad props to, I think it was Madison who posted this nice little vector video for us on the physics forum. They're still writing furiously, so I'm going to draw some shapes on here. Always like to circle best. Oh, freeform. All right. Oh, and by the way, I should have started with this. I am going to post this PowerPoint onto Canvas as well as this video. So if you just want to scroll through the slides real quick, all that info is right there. Scalars, I already mentioned, is simply a magnitude. That's all you really need to know about scalars right now. I'm not really going to test you heavily on that. It just has a value, no direction. Do make sure that you're comfortable with right triangle trig, though. So when an angle is marked on a right triangle, it'll have an adjacent side, an opposite side, and a hypotenuse. So make sure you've got SOHCAHTOA down pat, that the sine of an angle is simply the ratio of the opposite side over the hypotenuse. The cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. There's a lot more, and if you know what, if you're just feeling really bold and you want to go with a secant one of these days, just go with the secant and be proud of it. But I typically just stick to sine, cosine, and tangent and leave it at that. So speaking of right triangles, every single vector that you'll ever encounter can be broken down into horizontal and vertical components. Um, if you add additional dimensions, you can also get X, Y, and Z components. You can get up to however many dimensions you want and break it all down. But it'll make this look like a right triangle. So your original vector will typically be the hypotenuse of the triangle. Your x component will be just how far to the left or right did your vector travel without any of its up or down motion, and the y component will be the exact opposite. How far up or down did it travel without any of that left or right motion right there. And you make a right triangle out of it. So treat your original vector as the hypotenuse, and your x and y components are legs of a triangle. There's one quick exception to this, and that's this. If a vector is pointing directly to the right or to the left, or if the vector is pointing directly up or directly down, those ones are even easier to break into x and y components, because any vector that points horizontally has a y component of 0 and an x component of the full value. Same deal with leftward. With up and down, you've got an x component of 0 and a y component that's the full value of the vector up or down. And that's it. So that one's pretty simple to deal with. Not only do you need to know how to break vectors down into the various component parts, you need to be able to add a couple of different vectors together. So for example, I've got a very nice blue vector here that I met the other day named A, and I've got a slightly more surly vector that I've met over here that's green and is named B. When you add them together, you'll simply take the end of vector A, that becomes the beginning side of vector B, and the sum is just the very beginning of the first vector to the very end of the last vector, and that is it. To get this mathematically, you're going to have to find a total x component of this brand new vector. I'll call that Rx because that's the resultant's x component. You'll have to find the y component of the brand new vector. I'll call that Ry. And from there, you can use the Pythagorean theorem to get back to vector r itself. By the way, the x component is simply just the x component of A, which you can see, let's see, I'll draw that in purple. It's the x component of A, plus the x component of B. I'll draw that here, just black. Whoa, and that will bring you to your total x value. Same deal with the y, x component of A, or y component of A, plus y component of B will get you your total y. So here's how you'll do it. You'll look at each vector by itself. So grab A and pull that off to the side, and forget about B for a little bit. B doesn't matter. You are all about A right now. Break it into its x and y components using SOHCAHTOA. Odds are I'll give you something about the angle of this vector right here. Once you've done that and you have values for ax and ay, do the exact same thing for b. Take it, find its x component, bx. Find its y component, by, based on whatever angle is listed here. Then you'll add your x components together. That'll simply be ax plus bx. You'll add your y components together, and that'll just be good old ay plus by. And now you've got the resultant's x and y components. So all together, this equals my grand total x. This equals my grand total y. So Pythagorean theorem that to solve for your final vector. You can also use these x and y components to figure out any angle. If I've got rx here, ry up this way, and I've solved for final r, I can get, well, I've got this in the way. I can solve for this value theta using any trig function. Sine, cosine, tangent, it doesn't matter because I've got all three sides of the triangle, so I can use any of them. So speaking of vectors, there's a bunch of vectors that are going to be somewhat useful in this next upcoming unit. That would be your displacement or position. It's the distance between the starting position and final position. Your velocity, which is just speed and direction, also known as the rate of change of speed, also known as the slope of a position versus time graph. And acceleration. That's going to be your rate of speeding up or slowing down, or changing direction. Basically, it's just how is your velocity changing. So if you're ever in a situation that says constant velocity, you can immediately grab onto the fact that the acceleration in that instance is 0. Always. If it says constant velocity. They're still writing, so I'm going to tell you a story about my cat. Pretty much all winter, she would come up onto the bed in the middle of the night and then just flop on my neck, like straight up. I'm worried if I ever have a child, I'm going to have to keep the cat away from the crib because she's going to try to smother them, and it's terrible. So, and it hasn't happened all summer. She's typically just slept at our feet because it's a lot cooler there. Well, last night was the first super cold night, and sure enough, I had my cat scarf back, and it woke me up at about 2 in the morning, but it was glorious, except for how I couldn't really breathe all that well. That's my story, and it's a true one. A pencil sharpener? The closest pencil sharpener is on top of the teacher mailboxes right there. Just beyond that little wall. Keep going a little bit. Nope. Back this way. Just to your right. There it is. All right. The first physics equation you were introduced to was the position equation, or I guess displacement equation. So d is the object's position at time t. A lot of times I'll talk about that as the final position. D naught is the initial position, v naught is the initial velocity, a is the acceleration, and t is the time. The one thing about this equation is it does require a constant acceleration. So once your acceleration begins to change, then stuff begins to change a bit, but that's beyond the scope of this intro course. What I like about this is I can figure out a position at any moment only based on starting conditions, and that's it. And that's pretty powerful, actually, if you think about it. As soon as you know what some object is doing, in the absence of any extra force, you'll know what it's going to do pretty much for forever. Make sure that your units are straight as well. If you end up with a velocity in kilometers per hour and you multiply that by time in seconds, then you'll end up with that portion of the equation being in kilometer seconds per hour. Um, and that won't really help anything. So make sure that you go back to base units as often as possible. Anything that's a distance should be in meters. Anything that's a velocity should be in meters per second. Anything that's a time should be in seconds. Acceleration, meters per second squared, all that kind of good stuff. So pay attention to your units as you go. We also talked about the velocity equation. That's to calculate the velocity at any given time. Simply v equals v naught plus at. Once again, assuming a constant acceleration, all you need to know is the initial conditions, and you can tell me how fast anything is moving at any moment in time, which is pretty cool. Once again, pay attention to units as you go through your velocity equation. There's the combo equation, and this is the final velocity squared minus the initial velocity squared will equal 2 times your acceleration times your change in position. Anytime you see a delta symbol like this from now through the rest of class, because this is nowhere near the last time you're going to see it, that delta simply means an overall change. That's going to be your final condition minus your initial condition. In this case, since that's position, it's your final position minus your initial position. Um, so if you wanted, you could also just write the equation like this, and I'd have no problem with that whatsoever. D minus D, oh no, no, D not, there it is. Oh man, I had so much space to work with and I started so far to the right. Oh, it's late in the day, it doesn't count. Right. Free fall. Anything is considered in free fall the moment that the only force acting on it is gravity. That means, at least on Earth, that its acceleration is 9.81 meters per second squared downward. Um, and that's it. So any object where gravity is the only force, and a lot of you are going to point out that anything traveling through the air also experiences air resistance. So in truth, that's not technically in free fall, but we ignore air resistance enough that it's close enough. Um, and we'll ignore air resistance through most of this class. So even if something's moving upward, if gravity is the only force acting on it, it is in free fall. Ooh. A couple of things about free fall, which is most of the two-dimensional problems that you all have been dealing with when launching these cannons, looking at time of flight, all that kind of good stuff. Anything in free fall has zero acceleration horizontally. That means any acceleration is all going to be due to gravity. That'll be vertically 9.81 meters per second squared downward. That also means whatever your initial x velocity comes to be, that's your x velocity for the duration of the motion. That's its speed up at the top of its trajectory. That is its horizontal speed down at the bottom of its trajectory. That's its horizontal speed when it's halfway up to the top. It's like that the whole way around. Any object at the top of its trajectory has a vertical component equal to 0 and an x component equal to whatever it started with. Any object at the top has a vertical component of 0. And you can use this in problem solving as well. You're going to face a lot of problems that ask you how high up in the air something gets. And in order to solve that, you'll need to know that at this point, the velocity in the y direction is equal to 0 meters per second. From there, you can use the velocity equation, v equals v naught plus at, and 0 equals whatever your initial velocity in the y direction was. Let's say that's 11, plus negative 9.81 times time. Once you have the amount of time something takes, you can head to your position equations, your velocity equations, whatever else, and slap that value in there. So a lot of times the key to solving these problems is finding the time first. Once you have time, the rest opens up for you. So to get the actual height, I would then take that time up to the top. Oh, and by the way, this is just time to the top, not total time of flight. Just how long it takes to get to the highest point in its trajectory. I can take that time value, run it through a position equation using my value of time to the top, and I'll figure out the height that way. So that's why this last bullet point is super useful. It's just another thing that you can add to your known categories if you need to know something about a highest point. So speaking of that, whenever an object is not moving directly up or down, the first thing you're going to want to do is break its initial velocity into x and y components. So for example, here you've got a picture of a purple velocity vector that's pointing up and to the right. I'm not going to be able to use that velocity value in any equation, pretty much at all, until I break it into its x and y components. Once you have that, then I can head to my velocity, position, or combo equations and use this x value or use this y value. But I'm almost never going to use this initial velocity value in an actual equation. Almost never. Sometimes you'll need to solve for the initial velocity, like how fast was this thing moving at first. Then you can work your way backwards, get the x and y values, and Pythagorean theorem it to this velocity value here. It's exactly. I mean, this is vectors. Velocity is a vector. Yeah. So yeah, you'd break this down in the exact same way you'd break down your vector components. Which reminds me, on your WebAssign, there's a question I think that ends with how fast was it moving right before it hit the ground? To do that, just get its final x velocity, get its final y velocity, and Pythagorean theorem it to get its final actual velocity. Ooh. These are just the same equations, position, velocity combo. I just added subscript x's and subscript y's to them, just as a constant reminder that they only work in one direction at a time. So it's going to be no use to you using this purple velocity vector as one of your v naught values because it's not v naught x and it's not v naught y. So once you're in 2 dimensions, break everything into x and y first, then use the same equations and you're good to go. Okay. And I already mentioned free fall. This is kind of just rehashing what I've already talked about, so I'm just going to move forward. Make sure you know how to handle your motion graphs. So position versus time graphs, what does that actually mean? If I gave you a graph, could you tell me what kind of motion you're seeing? If I asked you about a motion, could you draw a graph for me? Yeah. For velocity versus time, a lot of times it's more complicated because now on your y-axis, you just have those individual speed values. Your slope is going to be acceleration, and signs are very important on your velocity versus time graph. So if your acceleration and velocity have the same sign, and by that I mean the y value of your velocity versus time graph, if that's positive and your slope is positive, because acceleration is slope, then you're speeding up. If your y value is negative and the slope is negative, you're also speeding up because both velocity and acceleration are negative. But if your y value is positive and your slope is negative, you're slowing down. And you can also tell that because you're heading straight toward a zero mark right there. If your velocity is negative, but your slope, your acceleration is positive, you're also slowing down. And you can tell because you're heading toward a velocity of zero. Velocity versus time graphs are a good deal more difficult than position versus time graphs. So maybe just look back at some of the activities we did interpreting that. I think your second lab involved that, and then we did that activity in class with the whiteboards as well. In general, to solve a problem, these are the steps that I recommend. It's going to vary physics teacher by physics teacher, but what helps me the most, first and foremost, draw yourself a picture. I honestly can't tell you how many mistakes could be averted by having an image to look at. I don't know why, it just makes your mind think in a different way. So draw yourself a little image of what's going on. If nothing else, on your, like I mentioned in class, I like to give tons of partial credit on the free response problems. So if nothing else, if you draw a picture and label whatever vectors you have on your picture, then I know you at least know what you're talking about at the start of this problem. And that's something, and that'll earn you some points back. The worst thing you can do is approach a free responsive problem, decide you don't know how to do it, and write nothing down. Because then I've got no choice but to say, well, 0 out of 10 points for this question. But if you write something, anything that shows me you know a little bit about the variables you're dealing with and how they're related to one another, then I can say, all right, well, you know a bit of the physics around it, just the finer details are giving you problems, and I can give you partial credit from there. So keep that in mind for sure. After you draw yourself a picture, label your coordinate frame. So where is the 0 meter position? Do you want it to be on the diving board? Do you want it to be on the water down below? Do you want it to be at the highest point of the trajectory? How are you going to work this? There's no right or wrong answer when you put your coordinate frame down. The only way you can be wrong at that point is if you then don't stick with what you set up for yourself. Once you've got that coordinate frame down, decide which direction is positive, which is negative, up versus down, left versus right. Again, there are no wrong answers, but any vectors you encounter that are pointing down had better match the sign of what you declared down to be, positive or negative. Any vectors that are pointing to the left had better match the sign in the x direction of what you called negative, right or left. Or sorry, had better match the sign of whatever was left, positive or negative. Yeah. Make a list of your knowns and unknowns. A lot of times the list alone can help you see which variables the problem is wanting you to work with. Then see which of those variables match up with the variables from your equations, and that can help you pick the right equation to work with. A lot of times there's not a single right equation, there's just some equations that are better than others for some problems. Making the list of what you know and what you don't know can help you work through that most efficiently. Make sure you've converted all your values to base units, meters, seconds, kilograms, etc. Find your equation and solve for your unknown variable. Keep track of your units, because probably the most common feedback that I give when I take off points is units, -1. So make sure that even if you don't know the correct way to get to an answer on your free response problems, that you know how to get units. As a big thank you for actually sitting through this whole review and listen to me jabber on. I'll give you a little hint as to what the lab question is going to be about. It's going to focus on lab 3. That was the one where you took the cart, set it loose to go down the ramp. Make sure you remember how you found acceleration, given your trend lines, given your position versus time graph, and your velocity versus time graph. How did you find your acceleration values? Don't forget how to find relative error. That's just your expected minus your observed value, the absolute value of it, so there's no relative error, all divided by your expected value. Make sure you multiply by 100 at the end to convert it to a percent. You're going to be using relative error for the rest of the labs from here on out for the most part, so it'll show up on occasional tests as well. Whew. That's all I got. So I'm going to let our two attendees finish jotting this down, but I'm going to go ahead and stop the broadcast. Bye, everybody. James says so long.